Okay, so now we're gonna do a capacitance combination which is purely parallel. So there was a first video that was already uploaded, and that was solving series combination of capacitances. This time we'll be using the same values, but the configuration will be the capacitors are connected in parallel. So if I remember correctly, we have the following given for that problem. We have C1 is equal to 5 nanofarad. We have C2, which is 7 nanofarad. We also have C3, which is equal to 6 nanofarad. And let's change the voltage. Instead of 1200 volts, let's just say the voltage across the terminal, say AB, is just 100 volts. So let's do it this way. So C1 now is 5 nanofarad. This is 7 nanofarad, and this is 6 nanofarad. So personally, I feel that doing capacitors in parallel is simpler than doing them in series. But of course, it depends on the problem that we have. So this is just a very simple solution to such. So I'm just using 3 capacitors in that parallel combination. So here it says required. What is C equivalent? So we know that C equivalent, so let's solve it. C equivalent is just equal to the sum of the capacitances. So that's C1 plus C2 plus C3. So this is straight out 5 nanofarad plus 7 nanofarad plus 6 nanofarad. So that will be 18 nanofarad. So that's our C equivalent or C total. Okay, now what about Q1, Q2, and Q3? Again, the guiding formula for capacitance will be this one. So it's capacitance equals charge over voltage. Therefore, if we're looking for Q, we can just say that that's just the product of C and V. So let's bring that to the next page. Let's just pull up one more. Okay, so we said that again, that's Q equals CV. So we're looking for letter B, we're looking for Q1, Q2, and Q3. And again, let's just draw it here. We have 3 capacitances. Okay, this is C1, C2, C3. This is 5, this is 7, and this is 6. And the voltage across, let's say that's AB, it's 100 volts. Okay, so let's continue. So if this is 100 volts across this terminal, it means across this terminal there's also 100 volts, there's 100 volts there, and that's 100 volts there. That's why I've said a while ago, personally, I feel that parallel connected capacitances are easier to solve. So it means that if I'm using Q1, then that will be just C1V, because across each terminal, that's just the same voltage. So what is our C1? That's 5 nanofarad times 100 volts. Okay, so let's just compute that. That's 5 times 10 to the negative 9 times 100. So that's simply 5 times 10 to the negative 7. And that's Q, which means this is now coulombs. Okay, so it follows. Or you can do it, no, that's just how to do it. Just make it simpler. So next is C2V. So this is 7 nanofarad times 100 volts. So this is now 7 times 10 to the negative 7 coulombs. Finally, Q3 is equal to C3V. So this is now 6 nanofarad times 100 volts. That would be equal to 7 times 10 to the that will be 6. Oops. Okay, that will be 6 times 10 to the negative 7 coulombs. Okay, so if you look at it, that's 6 plus 5 plus 7, that's around 18 times 10 to the negative 7 coulombs. So if you want to check, the QT now will be C equivalent times the voltage. So C equivalent, we already solved that a while ago. We had 18 nanofarad times 100 volts. And therefore, QT is now 18 times 10 to the negative 7 coulomb, which is also the sum of 6 plus 5, that's 11, plus 7, which is equal to 18. So that's how simple it is to solve capacitances in parallel. Again, just always remember, in parallel capacitances, okay, the Q's are equal. The Q's are summative, sorry. The Q's are the sum of the individual Q's, or the charges, and then voltage is equal, because for a given voltage across one terminal, it's the same voltage for all. And of course, the equivalent, it's just the sum of the capacitances. So that's it. So I hope this was very easy to understand. So there'll be more videos. I hope you like and follow the page. Thank you.